Hi everyone. Today we're going to continue our discussion on improper integrals from the day prior. So in this note sheet, we're actually going to go ahead and jump down quite a bit to the third page. Okay. Whoops, sorry, right there. Integration notes. Okay. So when we talked about improper integrals prior, we specifically focused on one of the bounds being infinity, right? Well, that's not, or a negative infinity, but that's not the only way to have an improper integral. So let's take a look. If f of x is continuous over an interval, let's call that interval a to b. Note that a and b don't have to be included, right? Just in the interval, we have a continuous function. Then our integral of the function from a to b, right? Basically, what we can do here is if a or b give us any values that are troublesome, right? Like undefined values or asymptotes, right? We can do the same thing we do at those x values that we do at infinity and negative infinity, which is we sub it out with some other variable. I'm going to choose c, right? And we just turn the integral into a limit. So it's limit as c approaches a. Now, since a is my lower bound here, I can only approach it from the right. And so this becomes the limit of the integral from c to b of f of x dx. Or let's say my right endpoint is the troublesome one, right? I will replace that one, right, with some, again, placeholder variable. I'm calling it c, right? Limit as c approaches b from the left. Remember, b is my right endpoint, so I can only approach it from the left. And so, again, we're going to do this, right, when either a or b is a problematic value, right? So again, think like undefined values or asymptotes at that x coordinate, okay? So we're actually going to just scroll up a little bit and we're going to do example 2 here first. So example 2 says to evaluate from 0 to 8 the integral of 1 over x minus 2 to the 1/3 or the cube root of x minus 2 dx. Okay, and so we have a little picture here, right? X minus 2 to the 1/3, right? Well, that's in the denominator, so clearly at x equals 2, we're going to have a vertical asymptote, right? At 0, everything is good. At 8, everything is good. So this is an integral that is not continuous in the interval, right? So what can we do with any integral, right? We can go ahead and break it up. And so that's exactly what we're going to do, right? So that's our first step. Let's go ahead and break it up, and let's break it up specifically where the trouble is, which is x equals 2, right? So we do integral from 0 to 2 of our function plus integral 2 to 8 of our same function, right? And now by having 2 as the upper bound and the lower bound of this other integral, now we can go ahead and use our same improper integral strategy. Let's go ahead and replace it with a variable, and we're going to do a limit, right? So for the first one, since 2 is my upper bound, this becomes the limit. And again, you can choose whatever placeholder variable you would like, right? Limit as b approaches 2 from the left, integral 0 to b of my function, plus, let's do the same thing for the other one. Again, the whatever you pick is your choice. Just, don't pick x. That's already accounted for in the integral, right? Limit as a approaches 2 from the right. This is my lower bound. I can only approach it from the right. Integral from a to 8 of my function, right? And so after doing this, right, now we could go ahead, right, find the antiderivative, do the fundamental theorem, right, and then apply our limits, right? And we would do that to both of these. Okay, so we're going to stop right here. We don't have to go through all the steps of necessarily finding those integrals and limits because that's similar stuff to what we've done in the past. Okay, so that's a little continuation of improper integrals. Okay, let's go back to the top. So I'm going to go back to the first page here, and let's take a look at the opener. So we're going to skip A because this is just refreshing on the hierarchy, which I trust you all to be able to do. Let's go down and take a look at B. Determine whether each interval converges or diverges. Okay, so I'm going to start with the 2 on the left because these are the 2 from our previous note sheet. Integral from 1 to infinity of 1 over x dx, right? I'm hoping we can recall that this integral will diverge, right? And so you can look back at the previous notes, right? We went ahead and evaluated this, right? And we did indeed get infinity, right? And so we say that this integral diverges, right? Remember, diverges means, right, that the integral does not come out to equal some finite number, okay? And infinity is definitely not a finite number. And how about 1 over x squared from 1 to infinity, right? Again, we did this in the notes in the last section. We did this integral and we got 1, right? And so 1 is definitely a finite number, right? And so that tells us that this integral converges. Now, based on these two from the last note sheet, can they help us evaluate these two new integrals, right? So the first one, integral 1 to infinity of 2 over x dx, is very similar to 1 over x dx, right? And so basically what I'm going to do here, right, is I'm just going to think about this as, instead of 2 over x being my function, right, what if I just took the 2 out? Now it's 2 times the integral from 1 to infinity of 1 over x dx, right? This is an integral that I already know the answer to, right? And now technically, we're doing something bad here, right? We're kind of treating infinity like a number, right? You would not want to really put this in your work, okay, right? But this is just to kind of get you the idea of what we're going to be talking about today, right? Well, what happens if I go 2 times infinity, right? Well, I can't really double infinity, right? So we're just going to say it equals infinity, right? And that's really just coming from what we did in the previous notes, right? If I'm going to take a function's integral that is basically going to be bigger than an integral that I know diverges, right? I know for a fact this integral diverges. We did it in the last note sheet. This integral is definitively bigger than the one that I know diverges because it's just 2 times my diverging integral, right? And so in general, we get this idea, right, that if we have an integral that is larger than a diverging integral, right, well, that means that this integral has to also diverge, right? If I know that 2 over x is bigger than 1 over x on this interval 1 to infinity, right? And I know 1 over x diverges, anything bigger than that is definitely going to diverge as well. Okay? And so we can kind of apply the reverse logic to this next one. What's another way of thinking of 1 over 3x squared, right? Well, I can just go ahead and take the 1/3 out, right? And now this is 1/3 times the integral that I know converges, right? What does this integral converge to, right? I know it converges to 1, and so therefore this is just 1/3 times 1, which is a third. Or in general, right, the function that I'm asked about is smaller. Now this is a little tricky, right? We have to remember the 3 is in the denominator, right? So the bigger the denominator, the smaller the fraction, right? 1 over 3x squared is smaller than 1 over x squared, right? Maybe not at certain values, but remember, x is going to infinity, right? So this is definitely getting smaller as x approaches infinity, right? Because the 3 is in the denominator, okay? Anytime I am asked about the integral of a function that is smaller than an integral that I know converges, well, then that one must also converge, right? And that's kind of the basic idea here, okay? And this brings us to one of the things we're going to do in this section and moving forward as well, right, is we're going to do little, I'm going to say the bad word, the P word, right? We're going to do little proofs, okay, right? We're going to do little proofs of whether or not an integral is converging or diverging. And one of our biggest tools with that is the direct comparison test. And so the direct comparison test is basically just rewriting this idea we did in the opener. Okay, so let's take a look at this. Let f and g be continuous functions on some interval a to infinity. Okay, and so we say if f of x is less than or equal to g of x over that entire interval, so less than or equal to, right, meaning f is a smaller function than g. And I know on our interval a to infinity that the integral of g of x converges. What it converges to is irrelevant, right? I'm not necessarily trying to figure out what these things converge to, right? I just want to know if they converge, okay? And so I know the integral of g of x converges, and I know f is smaller than g on that exact same interval. Therefore, the integral of f of x dx on this interval, a to infinity, must also converge. Now, be careful. Don't assume they converge to the same number, right? We're not actually worried about solving these integrals like we did in the opener. That's not necessarily the point here, okay? All we're trying to say is, do they converge or diverge? Speaking of diverge, let's flip it around. If f of x is larger than g of x, or equal to in some spots, right? Maybe all the way through, but then that would be kind of trivial because the functions would be the same. If f is larger than g on the interval a to infinity, and I know that g diverges on that interval, right? Well, then I know the integral of f on that same interval is also going to diverge. Okay, so again, just kind of what we said earlier, right? Smaller than converging will converge, larger than diverging will diverge. Okay, and that's what the direct comparison test says. All right, now that's a very big tool in our arsenal. Okay, another big tool in our arsenal, right, is going to be on the second page. But before we can do that, let's take a look at group problem 1. Okay, now be very careful with this one. Okay, this is the integral from 0 to 1, right? Now, if I go back to my opener, right, what did we talk about yesterday? We looked at 1 to infinity. You have to pay attention to bounds very closely on these questions, because again, a lot of the time you're not actually solving the integral, right? But if you pay attention to the bounds, you will be able to figure out whether an integral converges or diverges. Okay, so this is from 0 to 1 of our function 1 over x dx. Okay, so is this improper? Well, let's think about it, right? At x equals 0, right, we know there is a vertical asymptote, right? And so that's my lower bound here, right? You know, my function is undefined there, right? 0 is not in the domain. So let's see what's going to happen here. Okay, so the first thing I got to do is what we talked about earlier. Let's go ahead and rewrite this as the limit. And again, you can pick whatever placeholder variable you want. Just don't pick x, because x is accounted for. Limit as a approaches 0 from the right, because it's my lower bound. I can only approach it from the right, of the integral a from a to 1, excuse me, for 1 over x dx. Okay, and so we've done questions like this in the last notes, right? It's the same idea, right? We're going to go ahead and do our antiderivative first, and so that is going to give us natural log of x. Some of you might be going, hey, don't we need absolute value, right? In this case, we don't, because we're only dealing with positive inputs, okay? And so now, right, this is from a to 1, so let's go ahead and do fundamental theorem, right? Let's go ahead and plug those in. And so we know that the natural log of 1 is just 0, right? And so what happens to natural log as we approach 0 from the right? And so this is a good little time to just review a little bit, right? What does the natural log graph look like? Now, technically, this is negative natural log, but we can just flip the graph around. That doesn't matter, right? This is the natural log graph. This is a graph we should memorize for sure, right? What happens as we approach 0 from the right? This goes down, 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 right? All the way to negative infinity, right? And so it's negative, right? And again, as we approach 0 from the right, the function goes to negative infinity, right? And so this becomes double negatives, right? And so I get positive infinity, and that tells me that this integral diverges. Okay, so I told you guys to be careful, but we actually got the same answer, right, that we did looking at this from 1 to infinity in yesterday's notes. Okay, so here's the thing though, right? When you're looking at this from 0 to 1 or 1 to infinity, you can do all of this integration work, and you need to be able to do this integration work, right? But there's actually a way to tell what the integral will be, converging or diverging, without having to actually solve the integral. And that brings up something new for us. Our next kind of tool in determining convergence or divergence is the p-test. Okay, so the p-test, the p there is not for proof, the p there is for power. Okay, so if we are looking at the integral from 1 to infinity of 1 over x to some power dx, right? So that power, any real number, right? But actually, sorry, let me take it back. Any positive real number. We only really deal with positive real numbers, right? Based on what the power is, right, we know that this integral will diverge for all p-values between and including 0 and 1. Okay, so again, you can look at yesterday's notes, right, for 1 over x from 1 to infinity, right? We already proved that it diverged, right? That's why the equal to 1 is there. And if you do this for anything in between, like think about like 1 over root x or anything like that, right? You could go ahead and solve the integral, right? You're going to get that it diverges, okay? And when p is larger than 1, right, that is when this integral will converge. Okay, so think about like 1 over x squared, right? Another one that we did in yesterday's notes. Okay, 1 over x cubed, 1 over x to the fourth, same thing. Okay, now pay attention to the bounds, right? This is specifically for 1 to infinity. But one thing I want to add here though, right? What if this wasn't 1 to infinity, right? What if we were looking at this graph from like 2 to infinity, right? And let's say my function here is 1 over x squared, right? Yeah, there we go, right? That's actually less area, right? And so we're excluding this area from 1 to 2, right? But we know from the p-test and our work yesterday that when p is 2, this will converge, right? So what if I'm doing the integral from like 2 to infinity, right? And actually, the rules will still work, okay? So as long as you're starting, somewhere to the right of your asymptote, right? It could be at x equals 2, it could be at x equals 0.75, right? As long as you're going to infinity, right, these p-test rules will still apply, okay? Because the issue here is not necessarily x equals 1 or x equals 2, right? The issue is the infinity, right? The infinity is the thing that we're really focusing on, okay? Okay. Now, like the one we just did, right, the example above, right, integral 0 to 1, 1 over x to the p dx, right, this is going to diverge for all powers p that are greater than or equal to 1. So again, the one we just did above was p equaling 1, and it diverged. And if we did this for 1 over x squared, 1 over x cubed, etc., right, we would get that it diverges for all of those integrals. Okay, and then converging, right, is for the values between 0 and 1. Pay attention, right, there's no including here, okay, right, there's no equal to on this one, right, the equal to is at p equals 1, right, doesn't equal to on 0 as well. Okay, so p-test in combination with the direct comparison test, right, are two very powerful tools that we have. And so the last thing we're going to do here is we're going to take a look at example 1, and I'm going to show you an AP style free response and what I would expect from you. Okay, so evaluate this integral 0 to infinity 1 over x to the fourth dx. Okay, so 0 to infinity. Right away, you're going to notice, hey, Chief, none of our p-test rules are 0 to infinity, right? That's okay, because what did we already do on example 2, right? We talked about, hey, remember, we can go ahead and split it up, okay? And that's exactly what we're going to do, right? So the first thing I'm going to do, right, is I'm going to split this up into two integrals, right? Now, in this case, there's nothing wrong with the function at x equals 1, right? But x equals 1 is a good place to do it because I know I have different p-test rules, right? But remember, like we talked about here, it doesn't have to necessarily be at x equals 1, right? It would still work, like if I did, for example, at like x equals 2, right? all of the work I'm going to show you after that would still apply. Exactly the same, just, you'd have to update the bounds in my integrals, okay? But let's just keep it simple. Let's just do it at x equals 1, okay? So 0 to 1, 1 over x to the 4th dx, right? What does the p-test tell me for something like that, right? P is 4, which is bigger than 1, and so I know that integral would diverge, right? P equals 4 diverges by p-test. So something like this is what I'm looking for in your work, okay? Now, really, once you show me this, it doesn't really matter what happens with the other part, right? Because what I'm trying to do here is I'm trying to show whether this integral is going to equal a finite number. And if part of that integral doesn't give me a finite number, there's no way the whole integral will, right? So from 1 to infinity, 1 over x to the 4th dx, right? We can do the p-test, right? Yeah, that's going to converge, right? But it doesn't matter that this integral equals some number, right? If this one doesn't, because then I can't add them together and get a number, right? And so if even part of the integral diverges, right? Well, then the whole thing is going to diverge, okay? Now, in terms of justification, because this is something you will get asked to do, right? So that's the work I'm looking for. How do I justify? How do I write this out in a sentence? Okay. And I am expecting you to write a short sentence. Remember, not an English class. I don't need a paragraph. We're going to write a sentence. We're basically going to summarize the work we did, right? So what is that work that we did, right? So the first thing is, since the integral from 0 to 1 of 1 over x to the 4th dx diverges by the p-test. So right there, I'm talking about the p-test, right? P equals 4, right? That's what I need to say before I can use the p-test. And the integral that I am being asked to evaluate, right, is larger than or equal to, in some values, right, an integral that I know diverges, right? So those are two things that I know for sure, right? Because this is more area, right? I'm going past x equals 1, right? So this integral is definitely larger than the integral from 0 to 1, okay? And some of you might be wondering, hey, how do you know that for sure? Well, my function is always positive, right? 1 over x to the 4th. Positive inputs, right? I'm going to keep adding area. This is definitely bigger than the integral from 0 to 1, right? Larger than something that I know diverges by the p-test. Therefore, that's what the 3 dots mean. I can't remember if we've talked about this or not, but the 3 dots is a little shortcut for therefore, right? Therefore, right, the integral I'm being asked to evaluate must diverge by direct comparison. And if you wrote the direct comparison test, I would not take off for that, okay? So we will definitely do a lot more like example 1 the next time I see you all, okay? All right, so that's where we're going to stop for today. All right, thank you guys. I'll see you next time.